Now, after class last time, there was a few questions from some students about graded potentials. What, in fact, are graded potentials? As we look at the receptive segment, and remember that's dendrites and cell body, we have a lot of synapses impacting on those structures. We have a lot of neurotransmitters released. This is going to lead to ions in our postsynaptic cell. Get comfortable with that terminology. Changes of ions in our postsynaptic cell that's either going to cause our local membrane to become more positive or to become more negative. And that's going to happen at each one of these spots. You see the green, that's going to be a positive increase in our potential in that location. The red is a negative decrease in our potential in that location. Now, the difference between a graded potential and the action potential that goes all the way down the axon, the action potential, when you start it, it's going to finish. A graded potential, the further away you get from that location, the weaker it gets. Like if you throw a rock in a pond, the further out the waves go, the smaller they are, the weaker they are. The other thing that I want you to understand is these potential changes in that local environment are small and they only last a short period of time. And so when we look at one specific synapse and we look at our postsynaptic neuron in the membranes and the receptors, any change in our local potential is referred to as a postsynaptic potential. It can either be a positive increase or it can be a negative increase. But for right now, we're calling them a postsynaptic potential because it is a graded potential happening in the membrane of the postsynaptic cell, the receiving cell. Right? Presynaptic is the sender, signaler. Postsynaptic is the receiver, the listener. Now, our two types of postsynaptic potentials. We said it could either be positive or negative. You can figure out by the name which is which already, right? If you're at minus 70, and what is minus 70 in a neuron? Resting membrane potential. You've got to get up to the threshold for an action potential. And what is that number? Negative 55. That's the threshold to open which voltage gated channels? Sodium. I heard somebody say sodium. So if you want to make it easier to get to minus 55, you're going to make the membrane potential more positive. It's easier to excite those sodium voltage gated channels. And so we refer to that positive increase. Do you see that little positive bump there in our graph? That is an EPSP, an excitatory postsynaptic potential. Now, conversely, if we make the membrane more negative, we go from minus 70 down to maybe minus 75. Do you see how we're further away from 55? It's going to take a stronger stimulus, a stronger increase to get us to that threshold. And so this is referred to as an inhibitory postsynaptic potential. Now again, to make the membrane more negative, we can let more potassium out or we can let more negative chloride in. Either way, we're making the inside more negative. That is an IPSP. Do we see the differences? And when we look on our receptive segment, whether we're on our dendrites or whether we're on the cell body, we have a number of these happening at the same time. Now, neither one of these, IPSPs, EPSPs, reach threshold, so we're not going to send an action potential down the axon. But I think you can already appreciate if all you're going to get are these little small changes, you're going to have a bunch of them to change the potential up to our trigger point, up to our minus 55. All right. So that's a little bit about the receptive segment. what we have to do is we have to stimulate the axon hillock in that region. That's where the decision will be made. Do we send an action potential down the axon or not? So once again, all of those PSPs, positive and negative, that are impacting on the receptive segment, that's letting ions in or out of the cell. That's changing the local potentials. But again, think of the cell body as like a big washing machine. Everything's moving around. Ions that are coming in are moving all around. And they're all adding up. So we refer to that as the summation of all of the graded potentials. So if we look here, I mean, you may have 1,000, 10,000 of these synaptic knobs forming junctions with our dendrites and cell body. And when you add all of those together, what the membrane potential is at the axon hillock will determine whether we have an action potential or not. Because what do we have present in the axon hillock that is missing from our dendrites and from our cell bodies? There's something at the axon hillock, and it has to be there, otherwise you will not get an action potential, and that is not present in our dendrites or our cell body. It's a special voltage gated channel. Which ion? Sodium. Calcium's going to be that one that signals, and we'll get to that at the end, the transmissive segment. But for this, it's going to be our sodium voltage gated channel. So at the axon hillock, if we have enough EPSPs, and you see how here we have several in our graphic at the bottom, but we have them close enough together that before the first one completely resets. Now, what is it? What's the machinery inside of the cell that can take an EPSP and reset it back to resting membrane potential? What pump do we have that's doing that? Sodium potassium pump. It's working overtime to reset. But in our graphic, before the sodium potassium pump can reset the membrane potential from that first EPSP, we have another. And before that can be reset, we have another. Then we have another. See how it's kind of like they're standing on each other's shoulders? That's the summation of these graded potentials. And if we have one that gets us up to threshold, boom, we get an action potential. If we reach minus 55 millivolts in that initial segment, in the axon hillock, and we stimulate the opening of the sodium voltage gated channels, we get an action potential. What happens if that was our last EPSP and our membrane potential only gets to minus 56? What happens? Nothing. It resets because of the sodium potassium pump. So you either hit 55 or you don't. It's all or none. Once you start an action potential, it's going to go all the way to the end. If you never start an action potential, well, you never start an action potential. There's no wiggle room. There's no extra credit. There is no curving me up. It's minus 55 or nothing. Period. Now, this is just a few more illustrations of what is often called synaptic integration. And that integrative center is our cell body. Because here we have our positives. What are these positives called? What are they called? EPSPs, excitatory postsynaptic potential. Here we have a negative one, inhibitory postsynaptic potential. The summation is adding them all up. And where does it matter? The axon hillock, because of our sodium voltage gated channels. Now, once again, if we have one EPSP, just all by itself, little bitty baby one, no threshold reach, sodium potassium pump resets. But if we have two close enough together that the second one can stand on the shoulders of the first and we reach threshold, boom, we get an action potential. And we're going to explain that part of the graph coming up here in just a little bit. But that illustrates our action potential. Yeah?
So the closer
The closer they are, the better in some situations. And I'm glad you asked that, because look at this one. These are close together. And this EPSP would be big enough to reach threshold. But why didn't it reach threshold? Because you had an IPSP first, and it never reset before we started the EPSP. So for this particular cell, this particular neuron, it's getting a signal. Send the action potential. But it's getting a signal first that says, don't send the action potential. So who won? The don't, the inhibitory. So you see how it adds up? All the positives, all the negatives have to add up. And where it's calculated and deduced, what we're going to do is at the axon hillock. That initial segment. But if we reach minus 55 there, action potential is going to start. It's going to go all the way to the end. Once you start it, you can't stop it. The decision is whether you start it or not. That's the decision.
Why were those two switched? Like, why was the I1 first instead of the E1? Like, you can't control it.
It can be either or. For that illustration, it can be either way. Now, if the EPSP had gone first, you'd get an action potential. Right. Does everybody understand that? In this, if the EPSP had been first, it would have reached threshold. The IPSP would have been too late. So it's strength of the PSP, it's the direction of the PSP, how close they are together, and the sequence. That can make a difference. So that's a good question. All right, so our action potential, you've heard me say that a lot. And the action potential is this reversal of our membrane potential that's going to be conducted all along the length of the axon. We did that in our muscle cell, right? The sarcolemma, that action potential just flowed across our muscle membrane down into our T-tubules. It's the same thing happening here in our neurons. And we're going to look at this in a little bit more detail than we did in the muscle. It's just a better place to do that. So sodium voltage gated channels open at minus 55. We're going to reverse the polarity of our membrane. What is our resting membrane potential? Negative 70 millivolts. During an action potential, like in that graphic we saw, that line went way up. That line's going to go up to positive 30. So we're going to go from the inside being more negative to the inside being more positive. Just going to flip real quickly. But then before we finish, we're going to flip it back. So the two parts of our action potential are going to be the flipping and then the resetting. It's not quite that simple, but that's basically what we're doing. But as we look at the signal that's conducted along the length of the axon, because of the sodium voltage gated channels and the potassium voltage gated channels, each one's going to stimulate the neighbor, like doing the wave at the football game. And so they're going to self-propagate. They don't need another stimulus to start it. Each one is going to be a stimulus for the next. It's like the domino effect. The first domino to fall is going to be our axon hillock, that very first sodium voltage gated channel. Once you knock it over, it's going to knock all the rest of them over. In sequence, all the way down till we get to our terminal knobs. Now, in this conduction of our action potential, you can see we've got the reversal and then the reversion back. We're going to do this in two steps. The first step, depolarization, and the second step, repolarization. Now, at minus 70 millivolts, our resting membrane potential, since the inside is more negative than the outside, we're polarized. We have a positive out, negative in, like a battery. If we were at 0 millivolts, are we polarized? What term could you give to a membrane that had 0 millivolts? No, I mean, you're close. Neutral. Neutral. There's no charge difference. It's neutral. So our first step, starting at minus 70 millivolts, stimulating until we get to the minus 55 threshold for our sodium voltage gated channels. When the sodium voltage gated channels open, sodium comes rushing in, and it flips our membrane potential from minus 55 to positive 30. Now, here's what I want you to think about. As we go from minus 55 up towards positive 30, we're going to hit 0, right? We're going to hit 0 and go just clean past 0 up into the positive neighborhood. So what we're doing is we're going from negative towards 0. We are depolarizing. We're going from polarized to neutral. So ignore the fact that we bypass it. Because positive 30, I mean, we're still polarized, right, at positive 30? But we don't look at that. We just look at the fact of going from minus 55 up towards 0. We're losing the polarity of our membrane. Because we're letting all these positive sodium ions come flooding in. Now, I want you to note a couple of things here. And if you've printed out this slide, we're going to make some corrections. The sodium voltage gated channels, they open very rapidly. See, we have a closed sodium voltage gated channel at resting membrane potential. When we hit our threshold, they open. That little tongue sort of flips out and we open and sodium can come in. In our illustration, where it says closed, scratch out that word closed. Scratch it out. It's not closed. Closed is what we do over here at resting membrane potential when the tongue's in the way. But you see it's got a different shape? As soon as it opens, it inactivates. And when the sodium voltage gated channel is inactivated, sodium cannot go through it. It has the same function as if it were closed, but it's doing it in a different way. Principally because the voltage gated channel can't open and reset to the closed position as fast as it can be open and inactivate. And it has to happen very quickly. But it doesn't happen quick enough to hit 0. Enough sodium comes in to reach a positive 30, a more positive inside of positive 30. Okay? And that inactivated state of our sodium voltage gated channel, that's going to be extremely important in a couple of slides.
So will it always reach 30 or will it stop before it?
Since we're talking about action potentials, sodium and potassium voltage gated channel, it's practically always in that neighborhood. I mean, I've seen some books say positive 33. I've seen 32. It's always in that neighborhood. All right? So, sodium voltage gated channel, sodium comes in. And since we have all these neighboring sodium voltage gated channel, potassium voltage gated channels, the sodium coming in from the first as it spreads out is going to change the membrane potential under the neighboring sodium voltage gated channel to at least minus 55, and then it's going to open. When the sodium comes in, it spreads out, it's going to change the membrane potential of this one to at least. So do you see the domino effect? Each one's going to cause the opening of the next. And that's the propagation, the conduction of our action potential down the axon without any other stimuli. It's already preset, ready to go. Now, we've got the sodium, but we've also got the potassium voltage gated channels nearby, because the voltage gated potassium channels are going to repolarize. So if sodium took us from negative 55 towards 0 and positive 30, what do you think is going to happen in repolarization? It's going to take us back toward resting membrane potential. Because in the neighborhood of a positive number, now you can say positive 30, I think your textbook does that. I've never seen a definitive threshold for potassium voltage gated channels. I've always heard it just happens in the positive atmosphere, but never a specific number. But as we're getting toward the top of our depolarization, that's when our voltage gated potassium channels open again for a short period of time. Potassium comes flooding out of the cell. And as potassium leaves the cell, we're taking the positives and pushing them out, it's going to return us to a negative number. And so we're reestablishing the polarity, hence repolarization. So the voltage-gated potassium channels open and close, but not fast enough that we stop exactly at minus 70. Just like with sodium, we didn't stop right at 0, we kept going up to positive 30. Well, in repolarization, when we hit minus 70, even though we're not letting any more potassium out, it's going to get more negative than our resting membrane potential. And as soon as we get below minus 70, minus 71, minus 72, down to minus 80, we refer to that as hyperpolarization. Now, it's not a separate step. It's not a different channel that's happening. It's simply letting the potassium go out causes repolarization. And when our potential gets more negative than resting membrane potential, we simply call that then hyperpolarization. We're going to see it when we draw it out on a graph, and it'll make a lot better sense.
Is it the E number that is below negative 70?
Yes, if it's below your resting membrane potential, whether it's minus 75, minus 80, minus 85, minus 90, it's hyperpolarization. That happens at the end of our action potential. Now, since we're hyperpolarized at the end, we're at minus 80 millivolts. We can't stay there, right? If we're going to have another action potential come along, we've got to reset two things. What's the first thing we need to reset so that we can have another action potential? Remember, we're at minus 80. Where do we need to get our potential back to? Minus 70. So we need to reset our potential. So the sodium-potassium pump does a great job of moving ions around to reestablish negative 70 millivolts. Now, the sodium-potassium pump also helps us do the second thing that we have to reset or reestablish. What happened when we opened our sodium voltage-gated channels? Where does sodium go? It came in. When we opened our potassium voltage-gated channels, where did potassium go? It went out. We got too much sodium in and too much potassium out. The sodium-potassium pump has to reestablish our concentration gradients of sodium and potassium. And it takes just a little while at the end of our action potential to do that. So this is just our little diagram sort of summarizing everything. Sodium voltage-gated channels, depolarization, minus 53. See, even there I put plus 33. In the book I use for my pre-meds, it's always plus 33. When we open our potassium channels for the second half, we repolarize. But again, repolarization is for positive 33 to minus 70. Hyperpolarization is going to be from minus 70 lower. Does that make sense? It's all sort of happening because of potassium. We've got the re and then the hyper that's taking us from a positive back to a negative and slightly more negative environment. Yes, always goes hyperpolarized. And in fact, when you get to cardiovascular system in 239, your heartbeat is controlled because of that hyperpolarization period. So when your pacemaker cells in your heart go through an action potential and they overshoot and they hyperpolarize, you have specific channels that open during that hyperpolarization period, and they open and they cause you to have another one. And then when it hyperpolarizes the next one, they automatically open. Do you see how it just keeps it going? So yeah, you've got to have hyperpolarization. Now, let's draw this out graphically. All right, here's our membrane potential on the left. This is just our time. No, notice milliseconds. Okay, we can't quite think that fast, but milliseconds. So at the very beginning, we're at minus 70, and here at the end, we're at minus 70. What is RMP? Resting membrane potential. Now, in this number 2, when we're going from minus 70 up to minus 55, we're reaching the threshold for our sodium voltage gated channels. What could we call what's going on there in number 2? How else could we describe that? It's a stimulus. It's a PSP, but what particular flavor of PSP is that at number 2? EPSP. It's an excitatory postsynaptic potential that's making our membrane more positive, and it gets us to minus 55. From minus 55 up to positive 30, because sodium's coming in, what do we call that? Depolarization. Because potassium going out causes our membrane potential to come down to minus 70. See how this number 4 stops about right there? What do we call it? Repolarization. And then once we go more negative, and we stay more negative until we reset, number 5, hyperpolarization. And then our sodium-potassium pump returns us to resting membrane potential, and it reestablishes the concentration gradients for sodium and potassium. Write that in somewhere. We're not just making the number minus 70. We have to reestablish the very steep gradients for sodium out, potassium in. And the sodium-potassium pump does both, doing it at the same time. Sorry? It reestablishes the concentration gradients for sodium and potassium. Now, I don't mean to embarrass him, but if y'all haven't seen Justifer's new cover for his computer, you got to look at that. That's cool. It's an anatomical cutaway. That's sharp. That's sharp. All right. I have ADD. I get distracted pretty easy. Sorry. All right. Have we got our action potential? It's this wave, then, that you can graphically display flowing down our axon because of neighboring sodium and potassium channels opening and closing based on what the previous ones did. Now, here's another thing I want you to think about. With our action potential, let's say we've got our sodium voltage gated channel, potassium, sodium, potassium, sodium, potassium. When this, we'll say this is the axon hillock. Sodium voltage gated channel opens. Sodium comes in. Where does sodium go? Everywhere, right? It influences the potassium because it's a positive number. So depolarization, repolarization. Here we have a sodium voltage gated channel. Local membrane potential change to minus 55, opens. Sodium comes in. Where does sodium go? Everywhere. So why does the action potential not cause this sodium voltage gated channel to open and it go backwards? Why does it only go in one direction? The reason that happens is because what I told you to pay attention to back when we were talking about the sodium voltage gated channels not closed. What is it? It's inactivated. And so we're referring to a refractory period in which your neuron cannot basically propagate a new action potential. And during the period here where in 3 and 4, that's when our sodium voltage gated channels are inactivated. So in our illustration here with our classmates, when you have a sodium voltage gated channel that initiates the action potential, when it opens, it's going to quickly inactivate. So that by the time the neighboring sodium voltage gated channel opens, that one's still inactivated. It can't open again. Only the one down the line that is closed and ready to go can. That's what keeps the action potential going in one direction. It's not going to go backwards. Because absolutely no action potential for that one until it resets, which happens typically at the end of our repolarization period. Now, once we get to the end of repolarization, we could possibly start another action potential if we had to. But what's going to be the problem with starting another action potential when we're hyperpolarized? It's going to take more. Normally, here at resting membrane potential minus 70, How much positive change do we need to reach our threshold? Minus 70 to minus 55. What is that? 15? But if we're here at minus 80, what's it going to take? It's going to take minus 25. So your stimulus is going to have to be stronger. That's why we call it the relative refractory period. You can have another action potential, but the stimulus is going to have to be bigger than normal. If it's not bigger than normal, if it doesn't reach minus 55, no bueno, no action potential. Make sense? So the refractory period's partly the absolute built in so we get a unidirectional transmission. It doesn't ever back up. The relative refractory period is present because normally you're not going to have to do that many that fast. But just in case you have to, it's an emergency backup where you can in those situations.
Is the reason we have how quick we can move stuff based on the absolute refractory period?
The speed with which we can have more action potentials. Yeah, it's all based on that refractory period, how fast or slow that is. And in fact, your heart's probably the best example. I mean, tachycardia. And again, you're going to get this in 239. This is a freebie. Tachycardia is over 100 beats a minute. Well, you can get tachycardias upwards of 300 beats a minute. Now, you don't want to do that. That's a bad day. I mean, a really bad day. But you can, but you're never going to increase it any more than a maximal level because of that refractory period. You can't push the cycles close enough together because of the refractory periods. All right, so we're signaling down an axon. Action potential flowing like that wave around the football stadium. Sodium and potassium standing up, sitting down, letting our ions change. Now, normally, when we look at an axon that does not have any of our myelinating, insulating cells, that velocity is going to be about a meter per second. And that's just continuous conduction in an unmyelinated axon. Now, what's interesting is the larger the diameter of the axon, the faster the transmission of the signal. Now, I don't understand the physics behind that. But what's happening with our myelinating cells, and what's our myelinating cell in the central nervous system? Looks like an octopus, starts with an O. Oligodendrocytes. And Schwann cells, where do we find Schwann cells? Peripheral nervous system, that's a Schwann cell here. But if we insulate that axon, now we're going to conduct, not continuously, but what's referred to as saltatory conduction. These spaces that are between our myelinating cells and our myelin sheaths, these nodes, and again, this textbook's using some interesting sort of new terminology. Neurofibril node, that's always been the node of Ranvier, I guess Dr. Ranvier's name. But what you're going to do is the action potential is going to appear to jump from that node to that node to that node to that node. And because of that saltatory conduction, we're going to go from a meter per second to over 100 meters per second. It's almost as if that space underneath the myelin has been deleted. But the great thing about the area underneath the myelin, you don't have to have the voltage-gated channels, which are proteins which are energetically expensive to make and maintain. And since you're not letting ions in and out of here, you don't need sodium-potassium pumps. So you're using less energy. So the fact that you can, in fact, increase the signal 100-fold and use less energy, I'm liking that. More work, less energy. I wish they'd make cars like that. Faster, less gas mileage, better gas mileage, right? No, they're never going to do that. But do you understand how that works? But whether we're signaling fast or we're signaling slower, I want you to understand that our information is not necessarily just going to one place. So for instance, We can have, let's say, sensory information. Sensory information coming into our brain. We have a lot of sensory information coming in. We've got our sound coming in. We've got our vision coming in. And that's all converging on these integrative neurons in your central nervous system, in your brain. We just had Halloween, right? Anybody go on hay rides, scary walk? Go to the haunted, what is it, the haunted house or whatever? Huh? Oh, the haunted village, that's a good one too. But I think the JCs have a haunted house that you walk through. Have you done that? Okay, I'm a country boy, okay? I grew up in the country. Very few street lights even. You know you're a redneck if instructions to your house include turn off the paved road, right? So, but if you've ever been walking on one of these dirt roads at night, no moon, and it's dark, and you hear something over there, right? You hear it. You look at it as you're running away from it. I mean, maybe you can smell it. I don't know. You've got all of your senses trying to figure out what is that and how big is it. So that's your converging information. But you also have information that's going out. Now, we all know about the knee-jerk reflex, right? Get the little hammer, tap your patellar tendon, and your leg jerks. You're having the sensory input and the motor output on the same side of the body. That's pretty easy. One sensory fiber in, one motor fiber out. And if it's happening on the same side, that's referred to as ipsilateral. But you may not have done this little experiment, but when you become a parent, I promise you, you will. Especially if you have more than one child. You're up at 2 o'clock in the morning, staggering around to go find a bottle to feed your baby. And it's dark. You don't want to turn on the lights because then it'll wake you up even more. But the older kid left a toy on the floor, right? I don't know why they always make children's toys sharp, but they're all sharp. And what are you invariably going to do in your bare feet? Step on it. So here is an example of divergent information. When you step on something sharp, what is your reflex action? And don't say fall on the floor screaming and yelling. Okay, that's not the reflex. Your reflex is to take the weight off of your leg that's standing on the sharp object, but you don't fall because the instructions are also to immediately shift your center of gravity, contract the opposite leg to support the weight, right? It's like, oh, what did I step on? Right, that fast. So in that case, the divergent information, the sensory fibers coming to your spinal cord, the interneuron not only sends a fiber to your leg to say relax the muscle, take your weight off, but a fiber goes across your spinal cord to a motor neuron for your opposite leg, which is called contralateral, that says contract to support the weight. So do you see how you got one receptor said pain, and the divergent output came over to say get your weight off, and over to the other leg said add more weight here. So the information is not just going from one to one. You might be getting information from a lot of sources sensory-wise, and you might be taking a central nervous system motor cell and saying, let's tell a lot of places in the body what to do. You'll have a lot of this action going on in our next unit when we talk about autonomic nervous system. Not that you voluntarily control it, but you have a few cells in your central nervous system that comes out and tells these neurons in your 30 feet of small intestine what to do. That's probably the pinnacle of our divergent information. All right, receptive, initial, conductive. Now we get to the synapse. This is just like we saw with our neuromuscular junction. So we're already familiar with that. Postsynaptic neuron, that would be like our motor end plate, but in this case it's a neuron. In our presynaptic neuron, the action potential comes down. We have voltage-gated what kind of channels? Calcium, sound familiar? Calcium channels, calcium comes in. We have some signaling that goes on. Our vesicles fill with neurotransmitters in exocytosis. release the neurotransmitters into the synaptic cleft, and they bind to our chemically gated channels in our postsynaptic neuron, just like we saw in skeletal muscle. No real difference there yet. Now, once we bind our neurotransmitters to our receptors, our postsynaptic cell is going to have a PSP. It's either going to be positive or negative. So it's either going to be what? What's a positive PSP? Excitatory, or the negative? Inhibitory. I'm trying to get you accustomed to think positive E, negative I. Now, these neurotransmitters, there are a number of different neurotransmitters. I mean, maybe over 100. So depending on the neurotransmitter and depending on the receptor on your postsynaptic cell, that's what's going to determine if it's an IPSP or an EPSP. And so what was our neurotransmitter that excited skeletal muscle and is always excitatory for skeletal muscle? Acetylcholine. But in fact, if acetylcholine is used on neurons that stimulate cardiac muscle, acetylcholine is going to inhibit cardiac muscle. Not because acetylcholine is different for cardiac muscle, but in cardiac muscle cells, the acetylcholine receptor is different. And it leads to a different signal in which the membrane potential gets more negative. It's an IPSP. And it's going to slow down your heart rate. But there are times we need our heart rate to speed up, right? When we're walking down that dirt road and we hear that thing over there and it sounds really big, right? Well, in that case, we have other neurons that secrete norepinephrine. And norepinephrine, much like its cousin epinephrine, which is a hormone, that is going to get your body ready to do something really active. So your heart rate goes up. But it's interesting because norepinephrine causes your heart rate to go up, but it causes the smooth muscle in your digestive tract to do nothing. Because think about it. If there's something really big out there, Bigfoot or the swamp beast or whatever your imagination thinks that might be, is your body really worried about that Big Mac whether you digest it or not? All your body is saying is run, run. And I run slow, so I'm having to come up with a different plan too. The fight or flight, I'm probably a combination of both and not very good at either.